Now, we will discuss pulsating stars RRL rays. Like pulsating stars RRL rays and classical Cepheids, we will discuss in much more details as compared to other variable stars, because they are used as standard candles. These stars have fixed luminosities, and because of that they are used in galactic and extragalactic distance determinations. So, here is one figure which shows the period luminosity of RR star, type 1 Cepheid or classical Cepheid, and type 2 Cepheids or Virginis, W Virginis stars. Now, RR leaders have they have intrinsic luminosity lower than the classical Cepheids, and also their luminosities are much more less as compared to type 2 Cepheids, and because of this they cannot be detected at great distances as that of Cepheids. But all these RR rays, classical Cepheids, type 2 Cepheids, they obey some period luminosity relationship. In the case of RR ray, RR rays mainly they obey a absolute magnitude metallicity relationship. The period luminosity relationship is almost the slope is almost very negligible in the case of RR stars, but in the case of type 1 and type 2 Cepheids, there exists a robust period luminosity relationship. Now, RR rays are mainly found in the globular clusters. So, here is one animation of RR rays found in globular clusters M3. Now, this is the color magnitude diagram for a globular clusters, and this is the location where the RR rays are found in the HR diagram of a globular cluster. One can easily see that their luminosities are almost fixed, and this galaxy has a metallicity. For a fixed metallicity, the luminosities are almost depending on the metallicity, the variation in the luminosity occurs in the case of an RR star. And also shown are the different branches of the evolution of star in the globular cluster HR diagram. So, this shows the different parts like main sequence, subgiants, red giant branch, and they reach the RR star branch. This is RR ray, and when the star reaches this position, they burn helium in their core, and they are known as the horizontal branch stars. The general catalog of variable stars defines RR stars as radially pulsating giant A to F stars with periods in the range 0.2 to 1.2 days and light amplitudes from 0.2 to 2 mag in the V band. RL rays have been tracers of old low mass stellar populations within our and nearby galaxies. Their masses range from 0.6 to 0.8 solar mass. They are the core helium burning pulsating stars in the instability strip in the Hertzsprung-Russell diagram. RL rays have been used as standard candles to estimate the galactic and extragalactic distances. RL rays have been used as test objects for theories of the evolution of low mass stars and for the theories of stellar pulsations. The presence of RL stars in globular clusters facilitate the estimation of their ages and hence helps constrain the lower bound on the age of the universe. RL rays are divided mainly into two classes: RRAB, like light increases rapidly and decreases rapidly, but less rapid than the increase. Amplitude is from 0.5 to 1.2 mag, period is from 0.3 to 1.2 days, light curve is non-sinusoidal. Now, this A and B, they are known as the Bailey diagram, and they are now recently they are classified as RRAB. both of them are clubbed together and designated as RRF stars. On the other hand, RRC, in the case of RRC stars, a light appears to be always changing and with moderate rapidity. Light curve is mostly sinusoidal. Amplitude is less than 0.5 mag, period is from 0.25 to 0.5 days, and double mode RRD stars and second overtone RRA stars also exist. Now, one of the important things that we need to know is the metallicity, because in the case of RLA stars, RLA have a robust metallicity absolute magnitude relationship, and the period luminosity relation is not so much robust, and period luminosity relation is not used in the case of RLA stars. Hydrogen and helium are the two elements, lightest element created in the universe when it began in the Big Bang in decreasing order of abundance. All elements heavier than hydrogen are produced in the cores of the star as a result of the fusion by which they produce energy to shine. Metallicity is defined in the log scale as Fe by H is equal to log of Fe by H star minus log of Fe by H of sun. By definition, the Fe by H of sun is equal to 0. Therefore, Fe by H is equal to minus 1 denotes that the object of interest has 1/10 the amount of metals in it than the sun has, and Fe by H is equal to 1 would denote 10 times the metal content of the sun. The empirical relation connecting phi 3 1 in the V band period and the metallicity is given by Fe by H is equal to minus 0.5038 minus 5.394 P plus 1.35345 phi 3 1. This Fe by H, it is basically this is relation is an empirical relation, and where the Fe by H of a large number of RLA stars are determined using spectroscopy. The period of the stars are obtained from the light curves, and this phi 3 1 is known as the Fourier phase parameters, and it is obtained by Fourier fitting to the light curve of an RLA star. This phi 3 1 and this period, they are linked to the they are found to be linked up with this Fe by H with the metallicity of the star. Here phi 3 1 is equal to phi 3 minus 3 into phi 1, and they are obtained from the light curve of an RLA stars. And once the Fe by H is obtained by using the light curve parameters, then we can use a relationship of the following form, which is known as the MB Fe by H relationship, which is given as follows. And by substituting the values of Fe by H obtained from the light curve, one can obtain the absolute magnitude of an RLA star in the V band. Similarly, there are other relations in other bands also exist for RLA stars, and distance to an RLA star can be obtained by using this relationship known as the distance modulus in the V band, and here MB is the extinction corrected mean magnitude of the RLA star in the V band, and this is basically obtained from the telescopic observation. And here MV, suppose for a V band, so this should be replaced with this is the mean magnitude, MV will represent this A naught in the case of a V band. Similarly, for other bands like say in I band, it will be MI or mean magnitude in the I band. And this is the phase light curve. These phase light curves are fitted with a seventh order Fourier fit, and this the result of the fitting gives all the parameters. All let us say for seventh order Fourier fit, there will be 15 parameters, and these parameters can be used to find out, for example, the phase parameter can be used to phase parameter, and the period of the star can be used to find out the metallicity or Fe by H of an RLA stars. And once the Fe by H is calculated, we can calculate the absolute magnitude and hence the distance of an RLA stars. So, we should know some important facts about RL stars, that these are population 2 stars with a mass of the range of 0.6 to 0.8 solar mass, and they have luminosities of the order of 40 to 50 solar luminosity. And since they are very old population stars, their ages are more than 10 gigayear. RL arrays are found at all galactic latitudes, and therefore, they exist in the halo of our galaxy. They have very high radial velocities. They are low mass horizontal branch stars that are undergoing core helium burning. RL arrays obey a MB Fe by H relationship of the form MB is equal to A plus B Fe by H. Here is one table showing the some of the parameters of RL array and their ranges, and like for period is 0.2 to 1.1 days, absolute magnitude, mean value of absolute magnitude is 0.6 plus minus 0.2 mag, and effective temperature is around 7400 to 6100 degree Kelvin, and if log G, G is the gravity, surface gravity, and 2.5 to 3. Fe by H goes from 0 to minus 2.5 dex, and mass is 0 of the order of 0.7 solar mass, and the radius is of the order of 4 to 6 solar mass, as given in the book RL array stars by Horace A. Smith. Now, very important thing that we can extract out from the RL array star is the structure of galaxies, and like this is one of the pictures showing the picture of the halo of our galaxy. And since the halo basically contains the metal poor stars, and so this RL arrays, they depict the distribution of the halo in the case of a galaxy, and this requires so in order to understand decipher, in order to decipher the distance and also the 3-dimensional structure of any galaxy, we need to first find out the distance of the RL array using the procedure that we have described a few minutes earlier, and then after that we can use them to convert them into Cartesian coordinates by using some suitable coordinate transformations. And here red color point shows the center of the galaxy, and these are the different parts of the halo of our galaxy as characterized by the RL array stars. And the data for the RL arrays which is generated generated in the figure is taken from Catalina Sky Survey. Now, we will be discussing about the Cepheid, pulsating Cepheid stars. Like Cepheids are pulsating giants with a characteristic relationship between the luminosity and the time interval between the peaks in brightness, discovered by the American astronomer Henrietta Leavitt in 1912, and this luminosity period relationship calibrated with nearby Cepheids whose distances are known from parallax measurements allows the determination of a Cepheid's true luminosity from its time variation, and hence its distance from the inverse square law. Now, here is a figure, and which shows that as a period of a Cepheid increases, the luminosity of the Cepheid also increases, and this is quite distinct. So, the luminosity of the Cepheid can be completely determined once the period of the Cepheid is known, and like here in this case, the brighter Cepheid has a more pulsation period, and fainter Cepheid has a pulsation period which is lower. The distance can be determined from the following relationship: small m minus capital M, 5 log of d by 10 parsec. Here m is the apparent magnitude of the Cepheid, which can be obtained from the photometric light curve, and capital M is the absolute magnitude, which is nothing but the apparent magnitude at a distance of 10 parsec. This absolute magnitude is determined from the period absolute magnitude relationship, and this is period absolute magnitude relationship, or sometime called as the period luminosity relationship. Nowadays, this is known as, people are calling it as the Leavitt's law, who originally first described found this the relationship between the period and the luminosity of a Cepheid. And so, here the mean magnitude of the Cepheid, or the apparent mean magnitude, can be obtained by Fourier decomposition, that we have done it for the RL stars. And first, the light curve is converted into the phase light curve, and the phase light curve is fitted with a Fourier series, and then the A naught term gives the mean magnitude of a Cepheid in a particular wavelength band. Now, Cepheids are classified into two classes: type 1, or commonly known as classical Cepheids. Classical Cepheids, they are young stars, more massive than the Sun, with a metallicity of Z greater than 0.005. They are found mainly close to the galactic plane. And type 2 Cepheids. Type 2 Cepheids are old stars, less massive than the Sun, with metallicity less than 0.005. They are found at much larger distances from the galactic plane. Luminosity is 1 to 2 orders of magnitude less than the type 1 Cepheids. So, here in the HR diagram we can see that the type 1 Cepheids are located here in the instability strip, whereas the type 2 Cepheids are located below the type 1 Cepheid. Fundamental Cepheids, is one of the classification of type 1 Cepheids. Type 1 Cepheids are classified into different classes depending on which mode they are oscillating. Fundamental mode Cepheids have periods of the order of 1 to 200 days, but typical periods are a few days. Their light curves are usually asymmetric, with a rapid rise to maximum light and a slower decline, like the fin of a shark. Cepheids pulsating in the first overtone mode generally show smaller light amplitudes and more symmetric light curves than the fundamental mode pulsators. Their period range from 1 to 10 days, and second overtone oscillations produce nearly sinusoidal light curves with very small amplitudes, and these stars have period less than 1 day. So, we can see that the fundamental mode Cepheid, the periods are symmetric, and their amplitudes are somewhat larger. And here in the case of first overtone mode, the light curve is symmetric, sinusoidal, and their periods are almost between 1 to 10 days. And in the case of overtone, second overtone Cepheid, the light curve is sinusoidal light curve, but it has a very small amplitude, and the period of the star is less than 1 day. Type 2 Cepheids are further classified into 3 classes depending on the period. BL Hercules stars, and these stars have period of the order of 1 to 5 days. W Virginis stars, W Virginis stars have periods in the range 5 to 20 days, and RB Tauri stars, and for these stars the period is more than 20 days. These are some of the typical light curves of type 2 Cepheids taken from optical gravitational lensing experiment project. So, we have some of the important facts that we have learned about Cepheids. They are readily pulsating yellow supergiants. These stars have left the main sequence and are in a post core hydrogen burning and core helium burning. Type 1 Cepheids have typically masses of the order of 4 to 20 solar masses, and can have luminosities up to 10 to the power 5 solar luminosity. Type 1 Cepheids are population 1 stars, and their ages are more than 300 mega year, with periods between 1 to 200 days. The temperatures of this Cepheid are in the range 6000 to 8000 degree Kelvin. Because the luminosities of type 1 Cepheids are many hundred times more than the luminosities of type RL later stars, they can be used to determine distances of far off objects. but they can reach up to 40 megaparsec. Type 2 Cepheids are older population 2 stars with periods between 1 to 50 days. Type 2 Cepheids are low mass, the masses are in the range of 0.5 to 0.6 solar mass and have much lower luminosities than type 1 Cepheids. Both the two kinds of Cepheids obey a well defined Pareto luminosity relationship known as Levitt's law, and hence act as standard candles in galactic and extragalactic distance determinations. Due to their differential luminosity, type 2 Cepheids are used to establish distances within the galaxy and to close galaxies, whereas type 1 Cepheids can be used beyond the local group and are commonly used to determine the Hubble constant H naught. PL relations for galactic Cepheids are given by m lambda is equal to a lambda log p plus b lambda, where a lambda and b lambda these are the coefficients and they are calculated from the galactic Cepheid calibrations for which their distances are known from the parallax measurements, and apparent magnitudes are obtained using telescopic observations. Suppose a large number of Cepheids with apparent magnitude m lambda comma 0 corrected for extinction are discovered in a galaxy having similar metallicity as that of our galaxy. The periods of the Cepheids are known from their observed light curves. Then the Cepheids will follow a PL relation of the following form: m lambda naught is equal to a lambda log p plus b lambda prime. The difference m lambda naught minus capital M lambda will give the distances to each of the Cepheids in their galaxy. Now, here is an illustration showing using the calibrated Cepheid PL relationship to determine the distance modulus to a galaxy. And after a calibrated PL relation is adopted, this calibration PL relation is shifted vertically to fit the observed Cepheids data in a given galaxy, and the vertical offset provides the distance modulus of the galaxy. Why there exists a PL luminosity relationship for Cepheids? We can get the answer from Pareto mean density relationship. We know that Pareto mean density relationship is given by P is equal to is proportional to 1 by square root of rho, and rho goes as m by r cube. And in case of Cepheids which are located in the instability strip, and the masses of the Cepheids are very narrow, and therefore, the P goes as basically it goes as square root of r cube, and from this we can find that P to the power 4 by 3 goes as r square. Now, Stephen Boltzmann law tells that the luminosity is related to the radius and temperature. L is equal to 4 pi sigma square r square T to the power 4, it should be T to the power 4, and now there is a narrow range of T in the instability strip. So, because of that L goes as r square. Now, we know that L goes as 10 to the power minus 0.4 MB, where MB is the absolute magnitude in the V band, and r square, as already we have found that it goes as P to the power 4 by 3. Now, from that we can find that MB goes as A log P, therefore, MB is equal to A log P plus V. That is why we get a Pareto luminosity relationship for Cepheid which are located in the classical instability strip. Now, we can also suppose we have data in more than one band. Suppose we have Cepheid data in more than one band, let us say we have V and I band data. Then also we can find this distance modulus which are corrected for extinction. Now, this apparent distance modulus, it can be decomposed into a sum of true distance modulus and interstellar extinction, which accounts for the loss of light from the star, and this A lambda is given as r lambda into E B minus V, where r lambda is the ratio of the total to selective absorption in a particular wavelength band lambda, and is defined as r lambda is equal to A lambda divided by E B minus V. R lambda is taken to be taken from a given Redling law and has to be held fixed. EBB is the interstellar reddening along the line of sight, and mu lambda is defined as the apparent mean magnitude minus the absolute magnitude in a particular wavelength band lambda. M lambda can be estimated from the Fourier decomposition of the light curve, and the determination of M lambda, capital M lambda, relies on various empirical and theoretical calibrations. Since we have the light curve data of Seyffert's in two bands, and let us say we have data in V visual band and infrared I band, we can write down the above equation as mu y is equal to mu naught plus r I E b minus v, mu v is equal to mu naught plus r v E b minus v. Now, the two linear system of equations, they contain two variables, namely mu 0 and E b minus b, and hence they can be solved exactly. The solution of the above two equations yield individual values of reddening and true distance modulus as follows: E b minus v is equal to mu v minus mu I divided by r v minus r I. Mu naught is equal to mu I minus r I E b minus v, or mu naught is equal to mu v minus r v E b minus v. Distance can be calculated using the following relation. The distance in parsec is given by 10 to the power mu naught plus 5 divided by 5. Fixing the reddening law, namely the Carnot reddening law, and assuming R b is equal to 3.23, one can calculate A I divided by A b is equal to 0.61. Using this value, we find that E v minus I is equal to 1.26 E b minus v, and R I is equal to 1.97. The values of R b and R I are held fixed in the above linear system of equations, and we now show that the given relation, that the relations given by equation 6 can be reduced to a form of reddening free Masonite index. We find that the true distance modulus can be written as mu naught is equal to mu I minus r I E b minus v. Now, here we substitute the value of E b minus v, which is the reddening, and we get mu naught is equal to mu I minus r I subscript v I mu v minus mu I, where r I subscript v I is equal to r I divided by r v minus r I is equal to A I divided by E b minus I. In the present case, the value of r I v I is 1.563. Similarly, by taking the v band distance modulus, it can be shown that mu 0 is equal to r v minus r v subscript v I mu v minus mu I. The value of r v v I is 2.563, and the quantity is called mu naught is called the reddening free distance modulus, or it is the Masonite function. The above procedure is equivalent to a reddening free Masonite index. Now, we will discuss about Masonite index. The Masonite function can be defined as follows. It is given as capital W and is equal to magnitude minus R into color, where R is the ratio of total to selective absorption, which has to be obtained from a reddening law, and it has to be held fixed. Here magnitudes refer to photometric mean magnitudes obtained from the light curve of a variable stars. Different combinations of R, color and magnitude can be constructed to form W. Some of the examples are given by question 13, 14 and 15. The main advantage of using Masonite index is that it can be formulated intrinsically by incorporating the definition of total interstellar extinction as A v is equal to R into E v minus I, v is equal to v naught plus A v. This is the observed magnitude, this is the magnitude character for extinction, this is the extinction. And similarly, E of v minus I is defined as v minus I minus v minus I naught. Here v naught and v minus I naught denote the observed intrinsic visual magnitude and intrinsic color respectively. So, from the simple algebra, the Masonite function can be rewritten as W is equal to v minus R into v minus I. Now, we substitute for all these values, v is v naught plus A v minus R, v minus I is v minus I, this is V minus I is given as V minus I naught plus E of V minus I naught V minus I, and after some simplification we get that W is equal to V minus R into V minus I is equal to V naught minus R into V minus I, which is nothing but the W naught. Now, in other words, W as constructed from observed or red and colors and extincted magnitudes is numerically equivalent to W naught, as it would be calculated from intrinsic colors and intrinsic magnitudes. That is, W is independent of reddening. Another advantage of using W is that it reduces scatter in the W versus log P plot as compared to the scatter in the capital V or capital I band PL relations. The remaining scatter is due to the combination of photometric errors and the finite width of the instability strip. An equivalent definition of W with a combination of absolute magnitude and color can be formulated as W m is equal to m v minus r into m v minus m I. Then the distance modulus will be mu W is equal to W minus W m, and this is equivalent to mu naught is equal to mu v minus r into mu v minus mu y. Now, using equation 24 to obtain distance modulus is equivalent to obtaining distance modulus by fitting the W log P plane with the empirical W m log P relation. Here shows the optical near infrared Weissendt relations for LMC CFITs taken from Inno et al. 2013. Now, we will study about the period color relation for CFITs. How does it come? We know that the bolometric luminosity of all star including CFIT, they can be obtained using Stephen Boltzmann law of the form. Stephen Boltzmann law, as already we have seen, that it goes as r square into t to the 4 expressed in magnitude by taking a log on both sides and multiplying with minus 2.5. We find that equation 25 reduces to this form of equation. If T e, which is the effective temperature, it is mapped into an observable intrinsic color B minus V naught, and R is mapped into an observable period through a period density relation, and volumetric luminosity is substituted by monochromatic magnitude m v, then we have m v is equal to alpha log P plus beta B minus I naught plus gamma. Here m b and P are the only two independent variables. From equation 22, it can be concluded that W as constructed from observed colors and extincted is numerically equivalent to W. So, it would be calculated from intrinsic color and intrinsic magnitude. So, equation 26 can be written in terms of W as m W is equal to m b minus r v I into V minus I naught. So, m W is equal to alpha log P plus beta minus r v I into V minus I naught plus gamma. So, clearly if beta minus r v I is equal to 0, then W will not only be reddening free, but it will also be a dispersionless function of Fourier Delaunay with the slope alpha. Indeed, it appears observationally that beta and RBI must be quite similar in magnitude, given the fact that the dispersion in W is found to be very small, of the order of 0. Plus minus 0.08 mag. Therefore, the reddening free dispersionless function can be finally written as m W is equal to alpha log P plus gamma. This is the PL relation of CFIT of the form m is equal to A plus B log P. Those are PL relations for LMC fundamental mode CFITs, and the images are taken from the Inno 2016. And similarly, using multi-wavelength photometric data of classical CFITs, we can find out the reddening and the distance modulus, true distance modulus. This is one of the recent works that has been published in monthly notices of Royal Astronomical Society, and it deals with the determination of the relative distances, distance modulus and relative reddening of classical CFITs located in Large Magellanic Cloud. Large Magellanic Cloud and Small Magellanic Cloud are two satellite galaxies of our Milky Way, and LMC is located at a distance of 50 kiloparsec, whereas the Small Magellanic Cloud is located at a distance of around 60 kiloparsec from us. Now, this two figures show the reddening map of the Large Magellanic Cloud, and the map is constructed by using multi-wavelength classical CFD data, and whereas the right panel shows the reddening map of the Small Magellanic Cloud. These maps are quite in agreement with the all published reddening map of the two galaxies. Similarly, the structure of LMC, like the inclination and position angle of line nodes of LMC can be obtained by studying the distribution of Cepheids in the galaxy, and similarly the bar of the LMC is quite prominent from the distribution of classical Cepheid. Now, we will talk about Meyer variables. Meyer variables are believed to be in the last stage of AGB asymptotic giant branch evolution. They have larger amplitude greater than 2.5 Mach in the V band than other red variables, that is semi-regular variables or irregular variables, and can be up to 10 magnitudes. Meyer variables have stable periods of 100 to 1000 days, with mostly between 150 and 450 days. Meyers are highly evolved stars with masses between 0.6 and few solar masses. They pulsate in the fundamental mode. Meyers obey the following period luminosity relationship. This is the right curve of a Meyer variable chi Cygni, and changes in the visual magnitude, temperature, radius and volumetric luminosity are shown in this figure as chi Cygni pulsates. Now, also we have the pulsating stars like pulsating white dwarfs. So, as the white dwarfs cool, they pass through areas in the HR diagram where the pulsation can occur. A pulsating white dwarf is a white dwarf whose luminosity varies due to non-radial gravity wave pulsation within itself. So, because of the evolution, when the star evolved from the red giant, and this is known as the planetary nebula track, and the star pulsates when it passes through this track. Pulsating white dwarfs are classified into 7 classes: ZZ or DAVs, DQVs, DBVs, DAVs, and GWVs, ELMVs, and pre-ELMVs. We will be discussing about ZZ stars or DAV stars. ZZ stars, also known as DAV stars, are a class of variable star characterized by luminosity variations of 0.1% to 20% of their average luminosities. Periods are of the order of 30 to 1200 seconds. And the positions responsible for their variability are the result of ionization and then recombination of hydrogen in the outer envelope. Now, we will discuss about binary stars. Binary stars are basically they are mainly are the classes of extrinsic variables. So, in the case of a binary star, it contains two stars that orbit around each other about a common center of mass, bound together by their mutual gravitational attraction. Binaries are types classified into 4 classes: visual binaries, astrometric binaries, spectroscopic binaries, eclipsing binaries. So, we will now understand about the visual binaries. When the components of the binary star are sufficiently far apart to be resolved by an optical telescope, the system is called a visual binary. The brighter component of a binary is called the primary, and the fainter the secondary or companion. Visual binaries provide important information about angular separation of the stars from their mutual center of mass. If the distance to the binary is known, the linear separation of the star can then be calculated. Here shows the one visual binary Centauri, alpha Centauri A and B. Astrometric binaries. Some stars, if observed repeatedly over time, show a perturbation or wobble in their proper motions. When one member of a binary is too faint to be seen, observations of the visible star may reveal the slight wobble in its proper motion induced by the gravitational pull of its invisible companion. A star of this kind is called an astrometric binary. Example, Sirius. Sirius A is so much brighter than Sirius B that we can only see Sirius A. Sirius B was first detected by observing the motion of the brighter Sirius A. Spectroscopic binaries. If two components of a binary system are too close to be resolved by an optical telescope, they appear as a single star. The binarity of such a system can be inferred from the consideration of the spectrum, which will contain two sets of spectral lines arising due to Doppler shift as the star moves through their orbits around the center of mass. While the analysis of a star spectrum reveals its binary nature, this star is called a spectroscopic binary. In some instances, the spectrum shows the lines from both the stars. This is called a double lined spectroscopic binary. In other cases, only one spectral line is seen, the other star being too faint. We call the system a single lined spectroscopic binary. Here shows a diagram showing the spectroscopic binary system. Now, eclipsing binaries. So, when the orbital plane of a binary system is nearly parallel to the line of sight of an observer, that is with an inclination angle 90 degree, the binary components will be seen eclipsing one another. If such a system is aligned with respect to the earth, it is termed as an eclipsing binary. Eclipsing binaries are generally divided into three classes according to the shape of their light curves: Algol type, EA, beta Lyrae type, EB, and W Ursa Majoris, W UMA type binaries. This is an example of an eclipsing binary star. Eclipsing binaries are also classified based on Roshelov geometry. Binary systems whose component stars lie well inside their Roshelovs are called the detached binaries. The binaries in which one component fills its Roshelov and the other is well within its Roshelov is called a semi-detached binary. If both the two stars fill their Roshelovs and share a common envelope, then the binary system is called a contract binary. WMA binaries are also called contract binaries. Here is an diagram showing a detached binary, and this is the case for a semi-detached binary, and this one represents the Roshelov geometry of a contract binary or W Ursa Majoris binaries. So, masses of binary stars can be obtained by using Kepler laws. So, if two stars A and B revolve around their common center of mass C and have masses m A and m B respectively, if the orbital period is measured in years and the mean distance between the star given as A in astronomical units, then the sum of masses in terms of solar masses is given according to the Kepler's third law as m A plus m B is equal to A cube by p square, and this mass is given in terms of solar mass, and the ratio of the masses is given as m A by m B is equal to C B by C A, where this C A and this is C A and C B denote the distances of the stars from the center of mass. The two above equations can be solved to determine the masses of each of the component of the binary star if the values of the right hand side of the equations are known. Thank you.